Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 7 of our unit electrostatic potential and capacitance. In this class we are going to discuss about the electrostatic potential energy. In last class we were discussing about the same topic. This is the second class of the electrostatic potential energy. In the last class we have already discussed what electrostatic potential is, how can we define, and what is its basic formula of the electrostatic potential energy. So let's just quickly revise it and move to the more applications of the same topic. So when we discuss the electrostatic potential energy in last class, what we have discussed is that let's say this is the first charge q1, this is the another charge q2, the separation between these two charges is r. Then I can say a potential energy of this two charges, it's k multiplied by first charge multiplied by second charge divide by separation between these two charges. This is k multiplied by q1 multiplied by q2 divided by r. We can write this when we have assumed that potential energy at infinite is 0. This is the potential energy we can write. It's a k q1 q2 by r when we are assuming that potential energy at infinite is 0. Yes, so this is the potential energy when only two charges are there. But if more than two charges are there, let's say a first charge q1, another charge it's a q2, and one more charge it's a q3, and separation between this two is the r1, separation between this two is the r2. If this was the case, what should I do? What I need to do is I need to just make a pair of that. And to make a pair, what I need to do is just give them a number. If I give them a number, it's a first, this is a second, this is 3. Then I need to make the pairs of this, and it's a 1 comma 2, 1 comma 3, and 2 comma 3. So total potential energy of the system will be, it's a k q1 q2 divide by separation between 1 and 2, it's an r1, plus k q1 q3 divide by separation between this two, it's an r1 plus r2, and 2 comma 3, it's an k q2 q3 divide by separation between this two, it's an r2. This was the potential energy of the system. So this is what we have already discussed. We have already discussed the questions of reconfiguration. Yes, I hope you remember the whole strategy to work on the reconfiguration kind of questions. Yes, so let's begin with today's questions. Let's begin. But before we start, I request you guys to please have your pen and paper and do the questions with me. Yes, you are not just watching this, you are making a practice with me just now with the same questions. Let's do it. Now the question is that suppose initial system is looking like this. This is the q, this is the q, this is the q. The question says that find out work done require to shift any one of the charge to infinity. This is the question, that you need to find out and work done required to shift any one of the charge to infinity. So what can I do? What is your mind saying? What should be and what could be? Yes, is it a question of reconfiguration? Let's say that the separation between this is the, is it a question of reconfiguration? Yes, no, yes. So if it is a question of reconfiguration, what you need to do is that first you need to find out the ui, which is the initial potential energy. Then you need to find out an uf, and then you need to just simply do this delta u. That means you can write it as an uf minus ui or ui minus uf. Yes, so let's begin then. That this is the initial system having charges q and q. Their separation is a. Our first task is to give them a number. It's a first, this is a second, this is a third, and let's have a pair of this. It's a 1 comma 2, 1 comma 3, and 2 comma 3. It's a 1 comma 2, it's a 1 comma 3, and 2 comma 3. This would be my initial system. How my final system look like, how it would be. So if I wish that this charge should move to an infinite, so my final system should be looking like that. It should be this plus q, this plus q, and this has been reached to the infinite. This is at infinite. So their separation is a. So let's give them again a number. It's a first, but here no charges are there, so let's give them a same number, 2 and 3. If I make a pair of this, it's a 2 comma 3 alone. It's a 2 comma 3 alone. So what should I do? That if I simply write the potential energy, now both the cases, then what I can have is, it's an ui, then 1 comma 2, this is first, this is second, it is an k multiplied by q, that's a kq square divided by a, plus 1 comma 3, it's an kq square divided by a, plus 2 comma 3, it's an kq square divided by kq square plus kq square plus kq square. This is 3kq square divided by a. This is the initial potential energy of the system. I hope these things are clear to you. Yes. Now let's find out the final potential energy. What is it? It's a single term only. It's a k multiplied by this q multiplied by this q. This is kq square divided by a. Yes. Now what is the work done? The work done should be is equals to, let's say, final minus initial. This is the work done. Final minus initial. This final is kq square by a. The initial is minus of 3kq square divided by a. So that should be is equals to kq square minus 3kq square. It is minus of 2kq square divided by. This is the work done. Yes, I hope this should be your answer. Is it? Is it? Yes. So again, I need to find out work done by internal force and work done by external force. So let's again re-evaluate the diagram carefully. Look at this. Initially the separation between these three charges are a, and this is positive charge, this is positive charge. As both the charges are positive, that means they are going to repel each other. Yes, internal force is the force of repulsion, and due to this repulsion, this charge even has been shifted to an infinite. So what I can guess is that my force, or rather I should say is in my internal force, is acting in this direction. It wants that another charge should move to a very far away, and very far away it's an infinite. even the displacement of this charge is in this direction, even the displacement is in the same direction. So work done due to internal force should be positive. So what should I do now? Work done due to internal force should be, what was my answer? It's a minus of 2kq square by a. So now it would be plus 2kq square divided by a. Same way my charges were there, so my F external should behave like that. No, you need to attract each other, but particle has been displaced in this direction. Yes, so work done due to external force, so work done due to external force should be negative. So this external should be look like minus of 2kq square divided by a. This would be your answer. Yes, does it same? Is it? Great work. So ready to move the next question? Are you sure? Yes. Before we go through the next question, one more tricks and techniques could be there. Now look at this carefully, that what we have done is that I made an initial system, I make a final system, then I make a pair, it's a 1 comma 2 1 comma 3 and 2 comma 3, and I make a pair of this as well, 2 comma 3. Then I make to write initial potential energy of this, and then I make to write initial potential energy of this. So if I want that this is to be done by such a way that a certain amount of time can be saved, then why not to use that? So what I can assume is, or what I can write is that just I know that what I need to do, I need to perform UF minus UI. So can I do this? It's a 2 comma 3 pair minus of 2 comma 3 pair, 1 comma 2 pair, and 1 comma 3 pair. Yes, so this 2 comma 3 2 comma 3, this is 2 are going to cancel at this position only. So no need to write, or no need to just simplify this many things, this and then write down the this and then subtract it. Rather to subtract this pair at a very beginning level, that will save the time, and this time saving will help to us. I hope these things are clear. So I want you guys to follow the same procedure, that don't write the potential energy, just cut out their pairs from very beginning level, so it will save your time. But when you are using this trick, please keep in mind that your numbers in initial system and final system should remain the same. If you made a mistake, your answer would be wrong. Let's look. This is second, so this must be a second. You cannot do that my first charge has gone, so let me give the second charge as a first number, and let me give me this third charge as a second number. If you did it, then you will be having on a wrong answer. Yes, can you do this? Are you sure? Let's have a look. The question is that square is given, and here plus q plus q plus q plus q. Yes, their separation is, this is a, this is a, and all separation would be a, as it is a square, that you know. If they ask that find out work done require to bring a unit positive charge, let's give it a symbol q, to arrange at the center of a square. Yes, this is what they require. They want that find out the work done required to bring a unit positive charge q to arrange at the center of a square. So they might assuming it at here. This is initially at infinite, and you this people want that you should do something like that so that this charge q would be arranging itself at this position. So what should be the steps and what should be the procedure? Yes, you assume it correctly, that what I need to do is this should be my initial system having this many charges. It's a q q q q, and their separation is a, this is initial, and then this system is going to transform like this. This is q, this is q, this is q, this is q, and at center a charge q would be there. So this would be the final configuration, and now you need to just make the UF and UI, and the remaining stuff can be done. Yes, so let's do it very quickly. Let's do it. This is the initial system, plus q plus q plus q plus q, and this should be the final system, plus q plus q plus q plus q, and a charge is there, q. So let's give them a number. It's a first, second, third, fourth. So again I need to give the same number. It's a 1, 2, 3, 4, and one more. It's a 5. Now let's make a pair of this. Let's make a pair of this. So for the UI, my pairs will be 1 comma 2 comma 1 comma 3 comma 1 comma 4. Yes, next 2 comma 3, 2 comma 4, and 3 comma 4. I hope these things are clear to you. It's a UI. Now let's write down the pairs of the UF, final potential energy. It is 1 comma 2, 1 comma 3, 1 comma 4, and 1 comma 5. Then it's a 2 comma 3, 2 comma 4, and 2 comma 5. Then it's a 3 comma 4 and 3 comma 5, and it's a 4 comma 5. I hope, is it clear? Is it? Now what you need to do? What you need to do is you need to just simply work done is equals to delta u, and that would be equals to UF minus of UI. So if you write this, if you write UF minus UI, what you are getting is that you are going to subtract this, you are going to subtracting this initial pairs from this final pairs. So this pairs would be always cancelled out, 1 comma 2 and 1 comma 4, 1 comma 4, 2 comma 3, 2 comma 3, 2 comma 4, 2 comma 4, 3 comma 4, 3 comma 4. So the only remaining numbers are this much. Now can you visualize the thing that this is actually time saving constraint? Yes, this can actually help us. If I write down this pairs, if I write down the value of this pairs, this will make a lot longer for me. Yes, so let's do the remaining stuff. Let's assume that this is x. Yes, and we are going to just put up their value at the end. So this work done, this work done. Do you want diagram for a reference? So this all were the q, and this is the central charge, it's a q. So this work done, it's the remaining pair were 1 comma 5, it's a k multiplied by q multiplied by q divided by x. It's a 2, it's a k multiplied by q, q divided by x, plus k multiplied by q, q by x. plus k q q by x. I hope this is clear. Yes, so this would be 4 multiplied by k multiplied by q multiplied by q divided by x. As this separation, this is a, so the separation, the total separation between this two, it's a root 2a. And if I assume the half of the distance, it is root of 2a divided by 2, which would be an a by root 2, which should be my x. So let's replace the value. It's a 4kqq divided by x, and x is a divided by root 2. So that should be 4 multiplied by root 2 multiplied by k multiplied by q multiplied by q divided by a. This is the work done required. This is the work done required. Now what would be the work done required by an internal force, and what would be the work done required by an external force? Yes, initially charge is at infinity, and finally charge is at the center point. They must be having a force of repulsion, because this is plus q, this is plus q. Even though force of repulsion is there, particle has came a nearer to m, because initially it was at infinite and now it is at the center. So work done due to internal force, should be a negative, and same way work done due to external force should be a positive. I hope these things are clear to you. Is it clear to you? Are you sure? Can you make this kind of questions comfortably? Are you comfortable enough with this? Are you sure? So can you do this? Yes. So shall we move to the next pattern of electrostatic potential energy? Shall we? Okay, then let's move on to the next and new category of questions. What they have said is that, let's say here a charge q1 is there, it is fixed here. Charge q1 is there, it is fixed here, and another charge, again it is a positive, it is q2. Initially these two are having a separation of a, and at this position it is at rest. But this charge can move. What they ask is that this separation is 3a from initial position. This is from q1. Yes. So what they ask is that at this position q2 should be there. Yes. They ask that find velocity of charge q2 when it is at a separation of 3a from q1. This is what they require. I hope these things are clear to you. So let's redraw the diagram and begin with the questions. That initially the q1 is here, q2 were here, this where the separation a. You want that this q2 should be here. This is the separation of 2a, and in totality it is a 3a. Yes, it is the fix, so no chance to move on. It is at rest, but it can move, and you want this q2 at here. So what you can do is let's assume two positions. Let's look at this very carefully. This is what actually conservation of energy is all about. Let's look. This is position A, this is position B. Do you know that according to the conservation of energy, total energy of the system will remains conserved. That means total energy of the system will be a constant number. It cannot be destroyed and we cannot create any amount of energy. Yes, this is what energy conservation is all about. So what I can write is that total energy at location A should be is equals to total energy at B. While I say total energy, basically we are interested in two energies. It's a one is the potential, another is the kinetic. So what I can write is it's in potential energy at A plus kinetic energy at A, that should be is equals to potential energy at B plus kinetic energy at B. This is what my requirement is. Now what is the potential energy at A? What is the potential energy at A? While I say potential energy, I mean it's an electrostatic potential energy, and potential energy at A location, it's in K multiplied by first charge multiplied by second charge divided by separation between these two. It's a K Q1 Q2 by A. I hope this is clear. Is it? Great. Plus kinetic energy at A. Look at this. This is fixed, so no chance to move on. Even this is at rest. Can you show this? If it is at rest, this kinetic energy would be 0 because Q2 is at rest. This is 0 because Q2 is at rest. Now potential energy at B, at this location, it would be a K multiplied by Q1 multiplied by Q2 divided by separation of Q1 and Q2, it is 3A plus kinetic energy. I don't know because I want to find out the velocity. It's a half of the mv square. Yes. So if I solve this, then the things would look like half mv square should be is equals to K Q1 Q2 divided by A minus of K Q1 Q2 divided by 3A. Yes. Is it? Yes. So if I write this and if I solve this, now it's a, let's multiply and divide this with 3. It's a 3K Q1 Q2 divided by 3A minus of K Q1 Q2. So this is 2K Q1 Q2 divided by 3A should be is equals to half mv square. You have done all this to find out the velocity. I hope you remember this. It's a v square should be is equals to 4K Q1 Q2 divided by 3A multiplied by mass m, and for v I can write as it's a 2 under root of K Q1 Q2 divided by 3 multiplied by m into A. A is the separation, meter per second. This is the answer. Yes. Is it clear? Do you find this interesting? Do you? Yes, I like the concept of total energy is equals to total energy. Yes, a very good concept. Yes, if you know to apply energy conservation in a correct manner, your task would be easier in many of the units of the physics. That begins from the work power energy, then it's a gravitation, now it's an electrostatic potential energy, and even in the subsequent units of the physics of class 12 we are going to use it. So please remember this, you can always conserve total energy. Mind well, it should be an total energy. That means you can always write total energy is equals to total energy. You can always write this. If you write this, you need to always focus on the two kind of energy. One is the potential, another is the kinetic. Yes, while writing up the kinetic energy, you need to understand that if my object is in motion, it may be having kinetic energy. If it is at rest, it must be having zero kinetic energy. And potential energy, you can easily find it out that if it is an electrostatic potential energy, then it must be a K multiplied by first charge multiplied by second charge divided by divide by separation between these two charges, it's in k q1 q2 by r. And if the same thing can be asked with the gravitational potential energy as well, it's in gm1 m2 by r, and the rest I think you may do it. Yes. So does it clear? Does it clear? Can you do this? Can you do this? And shall I add something to this? May I? Okay. So let's add something. They asked that in the previous question, find out velocity of q2 when it is at infinite distance from q1. Even this can be asked when they don't want to say it's an infinite. They can ask that it is very far away from q1. So when they write this, you must understand that my examiner wants me to calculate for the infinite. I hope this is clear. Yes. So what would be the situation? The situation look like it's in q1. Now you can do this, and let's begin with this. It's an a. Now this q2 would be very far, and let's say this is the infinite distance. So this would be the situation, and I need to find out the velocity at this point. So what you will do it quick. Clock is running very fast. It's an a, it's a b. So what I can write, it's total energy at a must be is equals to total energy at b. I hope this is clear. Now when I mean a total energy, I am always interested in potential energy plus kinetic energy. So this is pe plus ke at a, that should be is equals to potential energy plus kinetic energy at b. I hope this is clear. Now potential energy at a, what is it? It's in k q1 q2 divide by a plus kinetic energy at a, what it would be, yes, it would be a 0. Why? Because at initial, in the previous data, they have said that q2 is at rest and q1 is fixed. Q2 is at rest and q1 is fixed. So this is k q1 q2 by a plus this is q2. How could I write this? It's in half mv square, but it is 0 because it is at rest. That should be is equals to potential energy at b. Now the separation between q1 and q2 is infinite, and as we have defined that for infinite, potential energy would be 0. Yes. So this is 0 plus kinetic energy at b is equals to half mv square. I hope you remember this. Yes. So this is k q1 q2 divided by a should be equals to half mv square, and my velocity square should be is equals to 2k q1 q2 divide by m into a. And if they ask v, then just have a square root of this. Let me do this. If they want v, it's just square root of this meter per second. That's it. You did it. Great job. I hope this I hope these things are clear to you. Is it? Is it? Are you sure? Are you sure? Okay. Let's move to the next question. Let's move. So can you do this? Are you? Are you? Will you be able to do this? Are you sure? Okay. So let's move to the next question. This says that find out electrostatic potential energy for the non-conducting charged sphere. Find out electrostatic potential energy for the non-conducting charge sphere on its surface, and on its center. This is the requirement. Yes, this is just the primary questions, and I will tell you that what the actual question may be. Yes, but let's begin with this kind of stuff only, that this could be the charged non-conducting sphere. The given charge is q1, the radius could be the r. As you know, this is the center and this is the surface, and now I need to find out the electrostatic potential energy. So what is the electrostatic potential energy? It is a work done required to bring a charge from infinite to particular location, and that all we know. But what should I do? Can I write k q1 q2 by r? No. So in this situation, very critical concept helps me. What is it? What is it? Do you know the potential? A basic formula of potential, very basic. A potential for a point charge. What can I write? Potential for point charge. What is it? We are coming in the same question only, but before I go through it, please help me this. Potential for point charge, what is it? Yes, it's a V is equals to kq by r. And what is potential energy? What is the potential energy? It's a k multiplied by q1 multiplied by, it's potential energy, it's a k multiplied by q1 multiplied by q2 divided by r. It's a potential energy. Let's say this is kq1. So if I observe this too very carefully, can I write that that potential energy is equals to q2 multiplied by potential? Can I write this? Potential energy is equals to q2 multiplied by voltage. May I? Yes. Can I take this freedom? Can I? Yes. It is the same thing. If you observe this very carefully, then you must know that voltage was defined as work done by charge, and it is the same thing we are doing. Yes. The only thing is we don't know that we can write a potential energy such as well. Yes. So what I can have is let's look now. The question is very easy, that this was the sphere having charge q1, this is the radius, and let's say this is the charge q that I need to bring from infinite to surface and from infinite to, let's say, center. So what I can write is it's a potential energy at surface. Potential energy at surface. So potential energy at surface can be written as potential energy on the voltage on the surface multiplied by charge, and that charge would be a q. So that should be k multiplied by q1 divided by r. This is the potential on the surface. I hope you remember this. Yes, multiplied by charge q. So this is k q1 q divided by r. This is potential energy on the surface. Yes, and next, potential energy at the center. It's a pe at center. So pe at center would be potential on the center multiplied by charge q. Now potential on the center, it is a 3 by 2 kq by r. Do you remember this? Did you? Are you sure? Okay, so that should be is equals to 3 by 2 multiplied by k multiplied by q1 multiplied by q divided by r. This is the potential energy at the center. Yes, yes. Can you do this? Can you? Can you? Are you sure? Yes. Okay. So, this is our question, potential energy at the surface and potential energy at the center. I hope these things are clear to you. Is it? Is it? Okay. So, let's move to the actual question. What I want to you people to answer, that let's say this charge, a small q, and here this is q1, that in the previous question, if charge q is at rest, find out change in kinetic energy when when it reaches to the surface. This is what the people ask, this is what they require. So what I should know this, that change in kinetic energy should be is equals to negative of change in potential energy. I hope you know this. It is the same thing, that change in kinetic energy plus change in potential energy is equals to 0, and this is the same total energy conservation stuff, nothing much more than that. So the change in kinetic energy, let's say final kinetic energy is 0, half mv square, as initial kinetic energy is 0, so no need to write half mv square minus 0. This is equals to minus of change in potential energy, this is uf minus of ui, and what I can write is it's an plus u initial minus of uf, this is equals to half mv square. So now you can write this at ui, initially charge is at the center, and at the center potential energy could be written as 3 by 2 into k into q1 into q divided by r. Now this is not new for you, you know this very well, minus of k q1 q divided by r, and the rest of amount of the solution can be done by you people. Yes. So can you do this? Can you? Are you sure? Are you sure with this? Can it be done? Yes. So shall we move to the next question? Shall we? Okay. I promise this is the last question of this unit, this lecture. Yes. So let's do it very quickly. As soon as you do it, this lecture will be over and you would be free. Yes. So please do it quickly, but as well as carefully. Yes. What they said is that there are two charges. Let me draw the diagram of this. There are two charges. One is here, it's in plus q. Another is the here, this is minus q. This is the center, their radius r, their radius r. This both the charges are moving on circular path having radius r with velocity v. Yes. What examiner requires, he requires find out first kinetic energy of the system Second, he requires potential energy of the system. And the third, total energy of the system. This is the requirement. They require potential energy, kinetic energy, and total energy of the system. Yes. So let's begin with this. This is the situation that this two charges are there. This is q, this is minus of q, and the radius is r. So how can I find out the kinetic energy? Yes, the electrostatic force between this two, it's in k into q into minus of q divided by square of the distance. It's a r 2r, so this is 4r square. And the centripetal force should be equals to mv square by r. So here the centripetal force required to move in a circular path will be provided by the electrostatic force. So I can equate this. So what I can have is, it's a minus of kq square divided by 4r square should be is equals to mv square by r. I hope this things are clear to you. Yes. So let's cut it out. It's a rr has been cancelled out. Now what I require kinetic energy, which is half mv square for a single charge. And at this present time I am having an mv square only. So let's divide this both by 1 by 2. So this is 1 by 2 minus of kq square divided by 4r should be equals to half into mv square. This is the kinetic energy of one particle. They asked that kinetic energy of the system, and this system having two people, so I need to multiply with 2. That's a 2 into half mv square. I hope this thing is clear to you. Please do not make a mistake and consider that this half mv square is of system. This is not of system. This is of an one individual person. So this is 2 multiplied by half multiplied by minus of kq square divided by 4r. Yes, as this is a force, this must be considered as a positive only. So this 2 would be a gone. This 2 would be a gone. And the kinetic energy of this system, kinetic energy of this system would be equals to kq square divided by 4r. Yes. Now what is potential energy? What is potential energy of the system? It is minus of k into q divided by separation between this two, it's a 2r. So that should be is equals to minus of kq square divided by 2r. This is the potential energy. Now what do I require? I require a total energy as well. So my total energy will be, total energy should be equals to potential energy plus kinetic energy. My potential energy is minus of kq square by 2r. My kinetic energy is equals to kq square divided by 4r. So that can be written as, this is minus of 2kq square by 4r plus kq square by 4r. So this is minus of 2, this is plus 1, so this remains as the minus of kq square by 4r. This is the total energy of the system. I hope these things are clear. Did you get the same answer? Do you? Great. Great work by you guys. Well done. I appreciate that. So let's wind it out here. As I promised that this would be the last question of electrostatic potential energy as well. Yes, from the next class we are going to learn a new topic. Till then, bye bye. Have a good day. Take care.